Hello and welcome back. In our last video, we finished the foundational work. We configured our dedicated network environment and set up the Ansible control node. We also used Ansible to deploy our NFS and DNS services. Today, we'll be deploying a few services in Docker containers on our Ansible VM. A quick heads up, we recommend you adjust your VM's RAM to 8 GB. This will prevent performance issues and ensure a smooth experience throughout the rest of the deployment. Okay, let's get into part 2, building a private software hub and automated OS provisioning. Here's the plan for what we'll cover today. We'll set up a private certificate authority using OpenSSL. Next, we'll deploy Apache HTTPD. It will serve as our reverse proxy in the future, providing a unified entry point for our Harbor and Nexus services. We'll then deploy our private repository services. Harbor will manage our container images, and Sonatype Nexus Repository CE will manage our other software and dependencies. And finally, we'll set up the PXEOS deployment service. This is the key that will allow us to automatically install the operating system on all our future VMs via the network. We'll wrap up the video with a demo. Okay, let's check out the playbook of the CA. This playbook is designed to be a complete solution. It will generate a self-signed root CA for our lab and then use it to issue a certificate for our Harbor service. Finally, it will copy the root CA certificate to a shared location for our other systems to use. Let's walk through the playbook. The vars section is where we centralize all our configurations. This includes our certificate subject details, the list of servers we're creating certificates for, and the local file paths. In the tasks section, we'll ensure that all the necessary directories for our certificates exist, and the NFS shared folder for storing the certificates is configured. Next, we'll generate a private key for our root CA. This is a crucial, secret file that forms the foundation of our entire trust system. With the private key ready, we can now create our root CA certificate itself. We'll use the OpenSSL command to generate a self-signed certificate that is valid for 10 years. Now for our services. This block of tasks will loop through our list of servers, Harbor in this case, and perform 3 key steps for each one. Generate a private key. It will create a unique private key for the Harbor service. Generate a CSR. It then uses the private key to create a certificate signing request, or CSR. This is a formal request for a certificate. Sign the certificate. And finally, it uses our root CA to sign that request, issuing a valid server certificate. The last task will copy our root CA certificate to our NFS shared directory. Okay, let's run this playbook to deploy our CA. Okay, the playbook is now finished running. As expected, it created the mylab.com folder under /etc/ssl/. Inside, it generated the ca.crt and ca.key in the root folder and the harbor.crt key and CSR files in the cert/harbor folder. It also copied the cacrt file to the NFS shared directory, making it available for other systems to access. Next, we'll deploy the Apache HTTPD service. This playbook is simple. It will ensure the HTTPD and mod-SL packages are installed, then update the configuration to make the HTTPD service listen only on our internal network address, 192.168.162.10. Finally, it will configure the firewall and start and enable the HTTPD service. Let's run the playbook to deploy the Apache HTTPD service. All right, with our Apache HTTPD deployment complete, let's move on to Harbor. Now let's take a look at the playbook. First, the playbook defines some variables we needed to deploy Harbor, and then configures the base environment. It installs Docker and Containered, then adds Harbor's certificate to tell Docker to trust our private registry. It will generate the daemon.json file using the docker daemon.ajson.j2 to instruct Docker to prioritize pulling images from our new Harbor instance. It also adds a record to the dnsmasq service to ensure our Harbor domain can be correctly resolved on the dedicated network. Next, the playbook sets up Apache HTTPD as a reverse proxy for Harbor. This allows us to access Harbor via standard ports like 443 instead of its default non-standard ports. For this to work, it will using harbor vost.conf.j2 to generate the harbor.conf, a virtual host configuration file. It also checks and enables a specific C-Linux policy, which prevents the system's security features from blocking Apache's network connections. Finally, the playbook executes the Harbor installation. It creates the necessary directories, then downloads and uncompresses the Harbor offline installer. Before running the installation script, we use an harbor.yml.j2 to generate the harbor.yml configuration file, making the entire deployment fully automated and ensuring Harbor is configured exactly to our specifications. Now let's run that playbook to deploy Harbor. All right, the playbook is done. Now we'll quickly edit the hosts file on your Windows system so you can access Harbor. First, press Windows plus R to open the Run window. Next, type the following command to open the hosts file with administrator permission. Finally, add this line to the very end of the file. Save and close the file. Okay. Let's begin by opening a web browser and navigating to our Harbor instance. Enter the full domain name and log in using the default credentials. Admin for the username and your password for the password. Once logged in, we'll configure an endpoint to pull the Sonatype Nexus 3 image. This allows Harbor to cache the artifacts from Docker Hub. First, click on Registries in the left-hand menu, then click New Endpoint. From the Provider drop-down, select Docker Hub. In the name field, type Sonatype/Nexus 3. Now click Test Connection. A success message will appear. Click OK to close the window. Next, we'll create a replication rule to start pulling the images. Click on Replications in the sidebar, and then select New Replication Rule. Give the rule a clear name, such as Proxy Sonatype Nexus 3. Check the Pull Replication mode, then select the Sonatype/Nexus 3 endpoint we just created from the Source Registry dropdown. In the Source Resource filter, enter Sonatype/Nexus 3 for the name, and enter Latest for the tag. Click Save to create the rule. Now let's start the replication. Select our new rule from the list and click Replicate. Harbor will begin pulling all the images and their layers. The job is complete once the success rate reaches 100%. With the replication job finished, let's make the replicated images publicly accessible. Harbor automatically created a new project named Sonatype. Click on Projects in the menu and select that project. Under the Repositories tab, you'll see the Sonatype/Nexus 3 repository listed. To enable public access, click the Configuration tab. check the public box of Project Registry, and then click Save. That's it. The Sonatype project and its repositories are now available to anyone without requiring authentication. All right, the next step is to deploy Sonatype Nexus 3. Let's take a look at the playbook. In the Variables section, we have all the required information, including the Nexus port, data directory, and FQDN. In the Tasks section, we first create the persistent data directory for Nexus, and then set the correct ownership so the container can write to it. Then, we use the Docker run command to deploy the Nexus container, pulling the image directly from our Harbor registry. Next, we'll use the wait for module to ensure the Nexus service is ready before we proceed. After that, we generate the Apache virtual host configuration file for our reverse proxy and add a new DNS record to DNS mask. Now that we've reviewed the playbook, let's go ahead and run it. Now that the playbook is complete, we need to update the hosts file once again to access Nexus. Just like we did for Harbor, you'll run the same command to open the hosts file, and we'll add a new line for Nexus. Now let's open the web browser and navigating to our Nexus instance. First, click the Sign In icon in the top right corner. A window will appear asking for your credentials. As Nexus tells us, the initial admin password is in the persistent data directory. Let's go to our server, find the admin.password file, and get that password. Once you have it, return to your browser and enter admin as the username and paste the password you just retrieved. Follow the on-screen wizard to set a new password. And then enable anonymous access to the repository. Now let's create our first proxy repository for PyPI, the Python package index. Click on the settings icon, then navigate to Repository. Click Create Repository and choose PyPI Proxy. We'll name this repository Proxy PyPI. In the Remote Storage field, enter or copy https://pypi.org. Check the box to use the Nexus Repository Trust Store. Click View Certificate, and then Add Certificate to Trust Store. Finally, click Create Repository to finish. We have now created our first proxy repository, ready to cache Python packages. Now we'll create the proxy repositories for Rocky Linux 9. We need a separate proxy for each of the core streams: Base OS, AppStream, and Extras. I've listed all the remote storage URLs in a text file. Let's create them one by one. Click Create Repository and select Yum Proxy. For the first one, let's name it Proxy Rocky 9 Baseos. In the Remote Storage field, enter the URL for the Base OS repository. Check the box to Use the Nexus Repository Trust Store, and click Add Certificate to Trust Store. Click Create Repository to save. Now, we'll repeat those steps for the next two Rocky Linux repositories. Finally, we'll create a proxy to cache packages from the official Docker repository. Now, our Nexus instance is configured to proxy the necessary packages for our upcoming deployments. All right, let's take a look at the last playbook for this video, the PXE playbook. This playbook automates the setup of a pre-boot execution environment to install Rocky Linux 9.6 on our target systems. In the variables section, we've defined all the necessary paths and network details for our PXE, TFTP, and NFS services. Now let's walk through the tasks section. First, we install the required packages like TFTP server, syslinux, and NFS utils to get the core services running. Next, we create the necessary directories for our NFS shares and the TFTP boot files. We also ensure that our NFS summary directory has the correct permissions for clients to write to it. We then prepare the GPG key for Docker and make it accessible via NFS. This allows our remote systems to authenticate the Docker repository. Please ensure that you have uploaded the Rocky Linux 9.6 ISO file to your Ansible control node and have correctly defined the Rocky_ISO_path variable with the full path to that file. The playbook then mounts the Rocky Linux ISO to a temporary location and copies all the installation files to the NFS shared directory. Once that's done, it unmounts the ISO to clean up. We then copy the essential boot files like vmlinux and initrd.img to the TFTP boot directory. We also copy the syslinux PXE boot files and use a template to generate a PXE boot menu configuration file. This is the menu that remote systems will see when they boot from the network. A key part of this playbook is generating a Kickstart file from a template and placing it in our NFS shared directory. This file automates the entire installation process on the remote machine, ensuring a consistent setup. Finally, we configure and export our NFS shared folders, start the TFTP and NFS services, and configure the firewall to allow PXE-related traffic. This ensures all services are up and ready to serve network boot requests. All right, let's take a deep dive into the kickstart.ks file. This single file is the heart of our automated deployment. It contains all the instructions needed to install Rocky Linux 9.6 from scratch and configure it to be a fully managed part of our environment. We'll walk through it section by section, starting with the basic installation settings. At the top, we have our core installation instructions. We've set the installer to run in a graphical mode, and the system will automatically reboot once the installation is complete. For network settings, the system will obtain its IP address via DHCP. For the installation source, we've specified our PXE server's IP address and the NFS directory that contains all the Rocky Linux installation files. Moving down, we define the disk and partitioning scheme. We're using AutoPart to automatically partition the entire NVMe 0N1 drive. We've also set the keyboard layout, language, and the system time zone. In the %packages section, we define all the software that will be installed. We've included the core minimal environment and added essential utilities like OpenEsh Server, NFS utils, and Python 3.11 with pip. For security, the root account is locked, and we're creating a dedicated user named Ansible with a pre-encrypted password. This user is a member of the wheel group. The most fun part of this Kickstart file is the %post section. This block of code runs a series of shell commands on the system immediately after the operating system is installed, allowing for deep customization. First, we have the internal certificate trust configuration. This script mounts a share from our PXE server and copies our internal CA certificate, placing it in the correct location for Docker, and mount the NFS shared folder contains the GPG file of the Docker repository. Next, the YUM and pip proxy configuration automatically reconfigures all of the system's package repositories. It backs up the original files and creates new ones that point to our Nexus instance. This ensures that all future package installations are cached by our local repository, significantly speeding up deployments. We also have the Docker Registry mirror configuration. This script creates a simple JSON file that explicitly tells Docker to use Harbor as its primary registry mirror. Then, in the deployment summary collection section, the script gathers detailed information about the new system, including its hardware and network interfaces. It compiles this data into a JSON file and writes it to a dedicated NFS summary share on our PXE server. This provides us with an automated, centralized way to track our deployments. Finally, we have the Ansible SSH key and sudoer configuration. This critical step automatically creates the .ssh directory for our Ansible user, copies our public key to the authorized keys file for passwordless login, and configures the sudoers file to allow the Ansible user to run sudo commands without a password. This ensures the new server is instantly ready to be managed by our Ansible control node. You can generate your own key by running the ssh keygen command. It will create a key pair in your home directory. Once you have the public key, you'll paste the entire content of that key into the Kickstart file, specifically replacing the content on line 273. Now let's run this playbook. The playbook has completed all the heavy lifting for us. For the sake of time, I've preempted some time-consuming tasks, such as uploading the ISO image, copying the files in the ISO image to our NFS share, and etc. Now let's start the demo. First, open VMware Workstation and create a new virtual machine. We'll name this one Demo. In the virtual machine settings, set the memory to 4 GB and assign 2 cores per processor. Click the network adapter and select our dedicated network, mylab.com. Close the hardware window, click Finish, and power on the virtual machine. At this point, the VM will perform a network boot and automatically connect to our PXE server. There's one optional manual step here. When the PXE boot menu appears, you can press Enter to start the installation immediately, or press Tab to edit option. If you choose not to intervene, the installation will begin automatically after a 30-second delay. This timeout value can be customized by editing the timeout in third line of the pexelinux.cfg.j2 template file. The rest of the OS installation process is fully automated. Once the OS installation is complete, you have 2 ways to determine the IP address. You can either log in directly to the system to check it, or you can find the IP and other system details in the Summary NFS shared folder, where the information has been automatically logged in a file named after the system's serial number. All right, let's verify everything is working as expected. First, we'll SSH into our new demo host from the Ansible control node to confirm that our SSH key works correctly, and that we can log in without a password. Next, we'll run sudo womi to check if the sudoers file was configured correctly, allowing our user to run commands with elevated privileges and without having to enter a password. Next, we'll use DNF to check if the new host can successfully pull packages from our Nexus repository. We'll run a few DNF commands to verify the Docker, Base OS, AppStream, and Extras repositories for Rocky Linux 9. Now let's open Sonatype Nexus 3 and see what's changed. You should see that our Docker and Rocky Linux 9 proxy repositories have cached some of the packages and metadata we just requested. Finally, let's check the PyPI proxy. Since we haven't used it yet, it should be empty. We'll run a pip install command to test it. Let's start by upgrading pip itself. After that, you'll see that the pip and simple have been created within Nexus. We'll then try to install a package like pandas to confirm that the Nexus proxy is caching the packages we request. After the installation is complete, let's refresh our Nexus page. As you can see, Nexus has successfully cached the Python packages we just requested. This confirms that our PyPI proxy is working correctly. This concludes our demonstration, and everything we've built in this video, from the initial deployments of Harbor and Nexus to the fully automated PXE installation of our new server, is working exactly as expected. In the next video, we'll dive into deploying a Kubernetes cluster and its components. If you found this video helpful, please hit the like button and subscribe. Leave a comment below if you have any questions or feedback. Your input is appreciated. Thank you for watching. I'll see you next time.